Hello. Sounds like a good time for. Oh, no, I'm sorry. Take that off. Seems like a good. Hold on. It seems like a good time for an update. We've had quite a bit of increase in activity in our online physics courses on edX, like AP Physics 1 and Mechanics Part 1 and 2. And for students new to the courses, I would say welcome. I hope you're finding them useful. You're going to find that sort of a hallmark of my courses is that I kind of ignore them, and I don't really answer questions, and I don't really fix bugs for months at a time, sometimes years at a time. And there's guilt there. I want you to know it bothers me. It gnaws. But given our new reality, I've been spending a lot more time on the courses, fixing them up. I think I'm completely caught up on questions and bugs and everything in those two courses, and I'm working fast to try to get E&M and Waves and Optics online as well. edX is also making some changes. There's a new portal where if you're an undergraduate registered at an accredited university, you can take edX courses for free once they sort of verify your situation. So I'll put a link to that down there if there's some edX courses that might be helpful. Rice Online is also making some changes. A lot more Rice classes are going to be available fully online this summer, including Intro Physics. So you could take the real Physics 101 or the real Physics 102 or our pre-med versions 125 and 126 for real Rice credit this summer. It's at reduced tuition, but still much more expensive than an edX certificate. But if you're looking for some, undergraduate summer credit, you should definitely check out Rice Online. I'll put that link down there as well. If you're running out of things to watch online, I have found something very interesting. It's called Physics After Dark, and it's a YouTube show being made by a guy named Dylan Berger, and I think he's sort of a Twitter guy, but now he has this YouTube show, and he just sort of interviews grad students and postdocs and professors about their research, and it's got a very kind of seedy late night vibe to it, the lighting and the music, and it's really hilarious. But it really is a good discussion of physics with the people actually doing it, and they talk a little bit about their lives and how they got into it. So it's a really great show. He's been doing them really often, so you should definitely check it out. I'll put a link down there as well. Okay, so that's a lot of plugging of things there. I also like to post these sort of fun challenge questions for you to think about. So the last one that was up was to figure out what these two things have in common in terms of physics. And several people did figure out what they both are. I think it's pretty clear one of them is beer being poured into a graduated cylinder, and you're watching the bubbles in the beer pop, and basically the foam gets lower and lower. The other is a cloud chamber. So this is something that was used in the early days of particle physics. You can see the little tracks of particles flying through the clouds and making little trails of bubbles that you can see, or trails of condensed droplets that you can see. Several people did figure out what those were. Let's see. So I think the first was Norbert Ziete, and then Kvantum Degenerik, and then John Buscemi all jumped in there and knew that those were cloud chambers. And they found interesting things that these two objects have in common. But what I was going for is they're both examples of exponential decay. So if you think about the foam, that's a collection of bubbles, and the height of the column is proportional to the volume of bubbles. Well, each bubble has the same chance of popping per unit time. Therefore, the ensemble of bubbles decays following exponential decay. This was actually studied and won an Ig Nobel Prize in 2002 for this method of studying beer. So I feel like that's pretty high honor. We should probably talk about it here. The other one is radioactive decay, which is exponential decay. That little thing in the middle is a piece of americium, or as we say in Texas, mericium. And its nuclei are decaying and releasing radioactive particles, or releasing radiation, and those are the particles that you see the little tracks. So they're both examples of exponential decay, just with vastly different half-lives. I believe one is probably a minute, and one I think is a few thousand years. So the new question is from this past, over the holidays, I was in San Francisco, and I was walking at night, and the streets are sparkling. And I don't think it's because they were clean. I think it may have something to do with optics. Okay, so one question is, why are the streets sparkling, as you can see there? But I think the more interesting optics question is, look at the rate of the sparkle. the rate of the sparkle is faster when it gets closer to you. So if you look off in the distance in the video, slow sparkle, look up near my feet, fast sparkle. So the question is, why do the streets sparkle, and why does the rate depend on how close you are to the sparkle? So that's the question. Good luck with all your online classes, and I'll see you soon.